We move to the next chapter. It is on active power and frequency. And input to the turbine would be, let's say, the steam, or it could be the hydro turbine. And then you also have a governor to regulate the amount of the steam and thus the develop power by the turbine. And since in this case you have the steam, so you have just the turbine is a steam turbine, and you have a boiler section, furnace in here, and you have a fuel control as well. And then the source for the fuel supply to the system. So all this part up to this section, you can say it will be as a mechanical system. And then from the soft point, right from the coupling point between the turbine and the generating unit, you have an electrical section. This will include the synchronous machine, synchronous generator. And on the machine you have an exciter to regulate the terminal voltage of the generator, and then to control the power, to damp out the power oscillations, there will be also a stabilizer in the AVR section of excitation system. So we have a use of a stabilizer, that is as a controller part. Then the generator is connected to the network. It could be a line, or it could be several lines, several configuration of the lines. And then this line will have the relays operation, mainly for the tripping purpose, tripping objective, whenever there is some fault disturbance, you can say. Then at the end of the line or the network, we have the load, and then these loads, they have the power drawn, active power and reactive power. In some cases, we also have provided a load relay, because in some cases, we need to control the frequency, let's say. So if we want to control the frequency of the interconnected system, and thus to achieve a balance between the source side generation against the demand from the load side. So if there is an excess demand which is not so can be tripped off, that we call it as load shedding. So depending upon the frequency dip, if I say the nominal frequency is 50 hertz, so depending upon a defined range of frequency dip from the nominal value, a predefined value of load shedding will be incorporated, it will be applied. So thus we have a load relay mainly for the load shedding purpose here, so that we have the system being interconnected and being having the frequency, and thus the system in a system operation in a stable form, you can say. So this could be the typical presence of several components in the system here that you can consider. Though we have a more complex, right, but it is not shown on this slide. Uh, now, previous slide, with the discussion of the previous slide. So as I said, you can see here that we have the turbine generator unit, your network, and the load. But the operation or the structure, as I said, it is a little bit more complex. And thus, if I have to consider that way, Then, as shown in this figure, you have this inside box. So here it represents the turbine generating unit control section. So you have a prime mover, uh, and then again the control. You have the prime mover and here. Then it is coupled to the generator, so the mechanical power being fed to the generator. Then at the terminal of the generator, we have some measurement, or let's say the speed signal. So it will be fed to the governor because we want to control the RPM, so the frequency of the signal, generator signal. And we also want to control the terminal voltage of the generator. So here we have another feedback to excitation system here. And this will regulate the amount of field current in the field circuit of generator here. So as you can see, or maybe I will discuss more later on. So you have two control loops. One is the speed control loop and another is the voltage control loop here. Then apart from this, you can see there is one more variable. It is as a speed or the frequency which is being given to excitation system. So can you guess what could be the use of this feedback signal in the excitation system? Anybody?
So to control frequency.
Frequency, for the control of the frequency, it is through the governor, which we have it here, right? But why we have this signal, which is being fed to the excitation system? If you remember from the previous discussion, we had one of the topic, that is the power system stabilizer. So if you refer the power system stabilizer, it may have the use of the feedback signal. It could be the speed signal, or it could be, although it is given here, power or the rotor angle. So the use of this is feedback signal is given to, it is for stabilizer design, which feeds the supplementary signal to the excitation system. So if you refer the block diagram of our system stabilizer, so it is here. So altogether, these two feedback signals, they are given to excitation system. One is for excitation system in the AVR, another is through the power system stabilizer to the AVR section. So we have two feedback signal to the overall excitation system block. Right, and so this is the section that we have it in the turbine generating unit. Then power output power from the generator, it is now fed to the network. So now we want to control the network as well. So we have another stage, or you can say the level of control being applied on transmission network, right? So this part is the control that we have on turbine generating unit. Next part of the control we want to have on transmission network. And there we have the reactive power control or the voltage control, because your transmission network is interconnected and the buses in the network, they have to be on a specified voltage, and thus it is very important that the voltage on these buses in the network, they remain within the limits. And thus, because you have the generators connected to these buses, you have the load connected to these buses, and thus to maintain the voltage stability in the system, right? You and whenever you have a, let's say, light load condition or heavy condition, more power drawn or light load condition, in that case the voltage at the bus will vary. We will discuss about this topic later on in another chapter. And thus, we need to have the voltage control at buses in the network, and thus we have the reactive power and voltage control. Another part is in some cases we also have the use of HVDC line, and the most of the AC network they are also connected to HVDC line. So thus we need to control the converters in the HVDC system, and then several associated controls to these transmission controls. So they are included here. Now at the transmission control, because we want the system being interconnected, right? We want a synchronism to be maintained in this interconnected system. So we do not want frequency instability. So we have to the use of frequency signal as a feedback here. And thus, if I say that there is a power flow from one area to another area, so we are actually concerned about what is the amount of the power flow in the tie line that connects the areas. And then what is the, we also want to know what is the amount of the power generated by the power plants or the machines and so on. So all these informations we have to know. So right, frequency, tile and power flow, and the power which is available at a given bus. So all these are measured. With those, there are several power plants. All right, there is not just one power plant. There would be several power plants. All right, here. So now each power plants, and then with the exchange of information about the frequency, about the Thailand flow, about the power generated by each power plant, right? We need to have a frequency control with economic allocation. That means we have to decide what could be the optimal cost of power generation by these power plants. We have to decide that way, and thus we apply the economic allocation of the power generation among the several power plants in the system, right? And then as you can see that when we have several network, let's say one power plant is here and then we have several power plants, and we have the information about frequency and the tile and power flow, then we, because the system we want to be interconnected, so we have a second level of control. This is actually referred as secondary level, or in some cases referred as supplementary control. So you can see here that this supplementary control is on the governor, that is to the turbine, you can say. So that means in the turbine control loop, in the turbine control loop, one is this one. This is actually a local frequency control loop or local speed control loop, or the inner loop on the governor, on the turbine governor system, right? This is inner loop. Then with the information, about the frequency, about the Thailand power flow with another power plant, there will be another feedback of the signal to the turbine or the turbine governor system, and that will be the outer loop for frequency control, and that will be that loop we call it as secondary loop or supplementary control loop here. So thus in the turbine governor system, you have two loops for frequency. One for the frequency control. One is the inner loop, that will be the local in the power plant. The another will be the outer loop, which will be the through between the network, between the systems, between the areas, and that will be through the supplementary control. Yeah. Then again, there could be, as you can see, that this supplementary control could be applied with several power plants here. So that's there will be several generating units and then the control here. So you have several generators and then the loads and the network, they are being interconnected. So we have several levels of control in the system, and that is the complete the control sections that we apply in the system here, in the power system here. So in this part of the chapter, we are actually concerned with the supplementary control for frequency here. So that will be the objective of this chapter that we will have now. Anything on this figure? Maybe if some points are not clear, we will have discussion later on, so that could be done. If not anything here, anything on this figure? No. So I move to the next one. Okay.
Excuse
So
me, sir.
maybe yes,
Hello.
yes, yes.
Sir, I want to ask that the supplementary control is provided at generating station or somewhere else.
Uh, in fact, this supplementary control between the two power plants, you can say. You have one power plant and then you have another power plant. Maybe in another figure it will be more clear. So inner loop, it is in the local power plant, but
Okay.
supplementary control loop, it could be between the two power plant, right? So depending
So
upon the
how how this can be achieved? I mean, this frequency is synchronized between two generating power plant, basically.
yes, okay, frequency information. So because the system is interconnected,
Okay.
so you
Yes.
have the frequency information, you have the tile and power flow in the system. So with those informations, uh, it is possible to apply a supplementary control, right?
Okay, sir.
Maybe
Thank you.
in the later slides you will come across, because the if the system is connected, right, then we want to have the scheduled amount of power flow in the tie line, right?
Yes, sir.
So what I mean to say, let's say area 1 and area 2. Okay, now if I say that area 1 has deficit in power generation, okay, it is less, the power generation in area 1 is less, and if the system is interconnected, then the power has to flow from area 2,
Yes, sir.
right? So
Yes, sir.
how much should be the power flow from the area 2 such that the frequency is within the limit? Okay, so that we apply, that we achieve with the supplementary control.
Yes, yes,
Okay,
sir.
okay.
Right.
So now with this slide, we have more in detail. So you can see here that we have the turbine, generator, and then the valve and the gate system and the governor part and the reference speed here. So this now, as you can see here, that from the shaft of the turbine, you have the measurement of a speed signal and given as a feedback to the governor system. So this is actually a local speed control, local frequency control, or we call it as primary frequency control, the primary stage frequency control, this one, right? Then since this generator is connected to the network, and the network transmission network have several generators or from several power plants, and then you have the load. So this generator feeds power to the remaining section of the network, which has some more power plants, which has some complex network interconnections and the power drawn by the load. So this is all here. Okay, now with this information, the system being interconnected, you get the value. In fact, this sign should be this reverse actually here. So we get the information about the tile line power and the frequency from the system, from the network here. This sign, we get the feedback of frequency signal and the tile line power. So this be here, right? Sorry for the. So we have the measurement of tile line power and the frequency from the network. And then we have a low system. We have a subsection, you can say, that we call it as AGC, automatic generation control. And this will feed signal to here, or that means the governor part here. So you can see here that there is another loop here. This is primary loop to the governor section, and to that's the information with the feedbacks information, feedback signal information of frequency and the tile line from the network. All right. To the AGC, it is again feedback to the governor part here. So this is a secondary loop here. This will be the secondary loop. So you have, this is your primary loop, and this will be your secondary loop, the second stage of control, you can say, or the supplementary control loop here. This is clearly presented in this slide from the previous one here. Okay. So we move to the next one. Now here, just to maybe I have discussed earlier also about this slide. So as you can see here that uh, we have the generator being coupled to turbine through the shaft, and from the generator terminal control. So this could be your governor part here, right? So your governor will regulate the amount of steam inlet to the turbine. So this is one loop applied on turbine generator unit. Then we have another loop with the feedback of signal, voltage signal from the generator terminal. And then it is you can say the exciter control part or AVR section part, which will control the field signal or the field current of the field circuit of the generator here. So thus for each generator, we have the load frequency control part or the frequency control part, in fact, here frequency control part, and then another part is your AVR section. So that is your automatic voltage regulator, which will control the voltage or the reactive power output from the generator. So in each generator, you have two control loops. One is this one, AVR control loop or the generator terminal voltage control loop. And second one is the frequency control loop. Here, remember that it is not the load frequency, but it is simply the frequency control loop, because as shown here, it is only the primary control loop here. All right. So it is basically the frequency control loop here, which will be meant to control the real power output. So in fact, as shown, you can see here that this loop and this loop, they can be independently operated. All right. So if I consider the system operation being perturbed for a small disturbance, for which the behavior of the generator and the complete system can be linearized, right? Then in that case, these two control loops, frequency control loop and the voltage control loop, they can be as a independently controlled. All right. But if there is a large disturbance on the system and thus including the generator, then since the generator is a nonlinear, we observe a nonlinear behavior, then in that case, in some way, there exists a coupling between the voltage control loop and the frequency control loop. Now, for this part of the study that we have on frequency control, we will concentrate only on small disturbance, and independent frequency control loop only, right? We are not concerned with the voltage control loop, and thus we will only have the discussion or the analysis of in the chapter only as a small signal disturbance here. Okay. So now maybe this is very commonly you can say that because your power system is very complex, right? And they are all interconnected, and we have several forms of disturbance, and thereby the control stage, the protection stage, they are all in different time scale, you can say. So you can see here that the protection part, the protection stage in the system, it will be of of shorter duration here. It will be in the range of milliseconds something here, right? Then, however, the voltage control, you can see that should be from milli to some few seconds or 1 second, few seconds here. Then the turbine control part, you can say it could be from few minutes to several minutes here. So it can last for longer duration, turbine control part here, right? To up to 10 seconds even. However, voltage control will be a few milliseconds to 1 second or 2 second, 3 seconds here. But protection is has to be much faster here. Then, as you can see here, this part of the turbine control is through the primary control loop. So here we have it from few minutes to several minutes here. But if you consider the secondary control loop for frequency and thus the tail end power, that could be from several minutes here, right? It could be from 10 seconds, you can say 10 seconds, or 20, 15 seconds, 20 seconds, up to near about 50 or 90, 80 seconds something, or maybe even more. So depending upon the dynamics of the turbine which are involved actually here, because the dynamics of steam turbine and the hydro turbine, they are a little bit different, right? So that's the tail end power, the frequency control, they could be in this range of time scale here. Then another part of the, because we are concerned with the tail end power and the frequency control, so we will have the scheduling of the power supply, because we want to have an economic allocation of the genetic machines, as I said. So we want, because we want to decide what could be the economical cost of power generation, that could be for of a much larger scale, right? So you can say it is one more than 1000 seconds something here, or much larger. It could be 15 minutes or half an hour or 1 hour. So nowadays we are discussing about applying the scheduling for every 15 minutes in some cases in some of the network. So that's that could be applied here. So you have the, you can see that in the your power network has to operate, and then there are several sections here, and they have to operate over a wide range of time scale here. Because if I say lightning occurrence here, because lightning occurrence is just some form of disturbance, right? It could be on a transmission network, and that will be in the range of microseconds here. And thus the protection against these lightning surges, that has to be in milliseconds something. Then any changes in the load disturbance and so on, or whatever the some kind of fault, so it will lead to the voltage control, or maybe if there is a load control, so that could be in this range of time scale. However, you can see here that power control or the frequency control, they are little bit slower as compared to the voltage control. So voltage control is, you can say, faster, because that we achieve either on the generator terminal here, or that will through the AVR, or it may be through some compensating devices on the buses. So they are little bit faster as comparable to the frequency control or the power control here, right? So maybe I have also referred this maybe this control that we have on generator in different form of the block diagram, but as you can see here that we have the generator so coupled to the turbine, and then we have the governor to regulate the amount of turbine power generation here. Then for the generator excitation control, as you can see, there is an AVR here. So we have the measurement of terminal voltage from the generator and then given as a feedback through AVR, and that will control the excitation. And then again, if you recall, again, there is a mistake here. This arrow sign has to be here actually, because we have a feedback of speed signal or the power signal here to the stabilizer, and then this stabilizer will feed an stabilizing signal, auxiliary signal, to the excitation system here. So in fact it has to be through the AVR complete part here, you can say. So that is the complete loop, the two loops for the frequency and the voltage control whenever there is some changes in the load side here. That is could be more way you can say that if I consider the frequency control. So you have a control command. Let's say how much power you want to generate. That is given on the turbine generator unit here, right? And then there is a feedback to the controller part here. Okay. And then you also have this, because there would be, because the generator is connected to the network. So the machine is subjected to some disturbance, and because this network has the load, so this load will result, the any variation in the load will in the system will result into a form of disturbance on the turbine generating unit, and thus there is a measurement of the signal which is as a feedback to the controller, and which will manipulate the signal with respect to, and it will feed to the manipulated signal to the turbine generating unit. So that is, you can say, the in terms of the overall operation for the generator control that we apply. So as you can see on this slide, how we achieve the frequency control. If you recall from the power balance equation, so whatever the power which is produced, that is equal to the amount of power drawn by the load, and including some losses in the network here. So that balance should exist. Now whatever the power which is produced, there would be some it could be plus minus, and then you need to have plus minus changes either on the steam side or on the water inlet to the turbine here, and that forms a basis for natural stability in the system here. However, so this is very simple, that whenever whatever the amount of the power which is produced, that you met for demand and the grid losses, and that will be as according to what is the amount of steam inlet or the water inlet to the turbine here. That form the basis for that form the basis for stability, natural stability. But If you refer to the characteristics of the power network, you can see here that frequency of the system depends upon active power balance. So that means active power of generation and active power of demand. That means the capital P, we say, amount of active power from the generation side and amount of active power drawn by the load side. So thus the frequency will be influenced. It will depend upon what is the balance between the two sides, generation side and the load side, active power balance. Now, generation and thus the frequency is sometimes referred as load frequency control or automatic generation control. But there is a slight difference between the two terms. Maybe later on we will discuss, right? And this terms mainly we apply when you have a supplementary control loop, when the system is interconnected, right? So thus you can say the control of generation or the frequency, that is more or less referred as load frequency control or automatic generation control. So this is could be a in general terminology that we will always use. Now the change in the active power demand at one point it will be reflected toward the system. So that means if the system is interconnected, right? And whenever there is a load disturbance at one of the bus in the network, it will result into a deviation. It will result into the change in the frequency of the signal. So that means if the active power demand or thus the load power, if there is a some change in the load power at a given bus in the network, in the interconnected network, that information will be reflected in the form of a frequency deviation in the system, and thus this could be a basis for the active power control or the frequency control in the network here. Now, but we always have our load changing because load is never constant. We always have a varying load and it is with time here. So that means the total power drawn by the consumer, it keeps on changing from time to time. All right. It is in fact in a day, right? And the power drawn by the consumer, let's say right from 6 o'clock in the morning till you can say in the afternoon period or in the evening or in the night, right? So it keeps on changing. Then again, the power drawn by the consumer varies as according to the day as well. The power on Monday, Tuesday, up to Friday, let's say. So these are the weekdays. Power drawn consumer on weekend, let's say the Saturday and Sunday, they are a little bit different way. So here the power varies on a week as well. Then again, power drawn by the consumers, it is as per the season. It could be the, you can say the winter season, it could be the summer season or any other season. So all right. So thus there is a seasonal variation of the power demand. So thus the power drawn by the consumers, it is highly dynamic, you can say. It varies not only throughout a day, but week or the months and as well as seasons. And thus the year as well somewhere. So it is highly dynamic here, and as a result, the power system operating point keeps on changing because we have to control the signals, we have to control the voltage, we have to control the frequency because we don't want any form of instability, right? We want a synchronism operation. Thus, we have to operate the power system network against this dynamic variation of the load demand or load disturbance. And thus the power system operating point keeps on changing. And as a result, it leads to deviation in the frequency here. It also leads to deviation in the voltage, but we will not discuss that point here because we are talking about the frequency control at the moment. So as a result, because of the changing operating condition, there is a deviation in the frequency, and as well as the power flow that would adjust between the areas here. So that is one typical characteristic here. Total generation does not change in step with the change in the total load. All because if I say there is a sudden load cut or sudden load increase, sudden load demand is being imposed on the system, but total generation, it cannot be changed suddenly at a step form. So it takes some time, and thus we need to apply the control so that it is effective within the desired time range, so that the nominal points are achieved, nominal signals in terms of frequency or the voltage are achieved. That is important here. Now, situation is seriously aggravated when governors are not in normal operation. If in case the governors, they do not operate as per the desire, or the governor settings are not effective or the perfect, then is a serious consequence or that could lie upon whenever the disturbance takes place here. Now, if you refer to this slide, uh, here I have it, how does the frequency has changed over the years in the Indian grid system, right? And you can see here, I have this slide from this report, and you can see that this is the 50 hertz scale. So in the Indian grid system, this is your desired frequency, 50 hertz. And you can see here that during the period 2004, somewhere, 2004 month, April, October. So we have at a regular months. So we have what were the changes. In fact, these are the mean values of the average, you can say average value of the months actually that is being given here in the figure. So in the during the period 2004, 2005, and 6 and 7 and so on, and even up to 12 here, up to 2012, you can see that the frequency average deviation was up to 48.8 or 49 something here. That was the average value of frequency deviation that we observe in these periods of years. But after, when we had the one national grid, when we had a one national grid, and thereafter you can say, because it was only during this period only we had it. So thereafter you find that the frequency deviation has the range, you can say, the range of frequency deviation, it is now as a narrow band, because over these years we had a large band of frequency variation here, right? But in this period of years, now we have the limited range of frequency deviation. So now we are able to keep our frequency deviation in a narrow range. You can see that. And thus, more or less, you can say the frequency remains within or across 50 hertz something. But earlier we had a frequency drop up to 49 hertz as well, or even as high as 50.4 something here. But that means, what do you understand by this graph? Can you anybody say? Yes, please.
So interconnection of the grids has led to more reliable system and maintaining the power quality.
Yeah, it can be one way you can say. That's the we are after when we have the formation of one national grid, we are able to have more effective power exchange between the system as per the demand, right? And then again, we are you can say able to have narrow range of frequency actually, and thus you can say we are able to have effective control operation in the integrated system. So this is, if we are able to have a narrow range, so that means we have an effective control being applied in the system. Yeah, and that has been achievable over the years when we had formed the national grid. Yeah, one national grid, that we can say.